Okay, equivalent load systems. So our topic is so I want to find the equivalent load system. In fact, when I have external loads, it can be a force or a moment. I want to simplify the problem. Therefore, you may have infinite number of forces, infinite number of moments, or you may have hundreds of moments acting at different points, and hundreds, maybe 50 forces acting at 50 different points. So you want to simplify the problem, and you want to solve the problem in order to determine the reaction of the system. So first thing is to reduce the system of loads. Okay, so how can we do it? Now, in fact, when we have a resultant force, Fr, we denote the resultant force with Fr. In fact, it is quite straightforward. Sum of the forces, external loads, external forces, acting on the body is equal to the resultant force. And moreover, how can we determine the resultant moment? In fact, every object has a center of gravity, and let's say that this is at point O. Now, I want to reduce the whole system of loads to a one force and a moment, which acts at the center of gravity. So let's say that this is Fr. Okay. So sum of the forces, the magnitude of the Fr has to be equal to sum of the forces. And in fact, since forces are vectorial quantities, I can easily sum them up. And I will form a vector I can easily obtain the resultant force vector, Fr. Now, the point is how I can obtain the resultant moment. Now, each force generates a moment at point O. So remember that it is Re position vector multiplied by the force vector. So Re vector product Fi will give me the moment generated by this force. If I sum them up, I will obtain the MO, the moment vector, which acts at the center of gravity. Now, certainly, I may have some moments acting on the object at different points. Let's say that these moments are MC, sum of the moments. And as a result, moment at the center of gravity is equal to the sum of the moments acting on the object plus sum of the moments generated by the force. Now, this is first reduction. Okay, so what else? Now, just imagine that we have forces acting on an object, and these forces are perpendicular, just forces. How I can obtain the equivalent load system at an arbitrary point if the forces are perpendicular to the object or perpendicular to the area that it acts. Now, the point is very simple. O is our center of gravity. for example. In fact, if you use the right-hand rule, you will easily see that moment is an in-plane. So these lines are position vectors. So this is R2, for example. And this is R1, for example. In fact, at the center of gravity, you will have the resultant force, which is perpendicular to the area or surface. Now, because of the position vectors and force vectors, for example, this will have a moment of this direction. This will be m1, which is inside the plane, and this will have the moment vector of this direction, right, which is m1. This is m2. So you will see that all the moment vectors are in the plane, as is the case in position vectors. Certainly the resultant moment vector will be inside the plane, and it will be perpendicular to the FR. Okay. Now, this moment vector will have a direction. Let's say that it lies on the axis of B. Of course, I can determine a point. Okay, let's say that this point is D. This distance is D, I mean. Okay. So there's another axis which has a distance of D, on which the moment is 0. This basically means that, so remember that here I have the moment MO. In fact, this FR will tend to rotate this object and generates a moment of FR multiplied by D, which is equal to the MO, right? And along this axis, if I move, or in other words, if I move the resultant force to on this to a point on this axis, certainly the moment generated will be 0 on this axis. The moment on this axis is 0. So this system is equivalent to this one, and this is equivalent to this one. In fact, how I can calculate the D then? Certainly, moment at the center of the gravity, the magnitude of the moment at the center of gravity divided by the magnitude of the resultant force, in this case, will give me the distance D. Okay. So there may be other cases. In fact, in some cases, the resultant moment can be out of the plane. It's probable. So may not lie in the plane of the plane that the forces are acting on. In that case, certainly we have an arbitrary moment. Therefore, we can decompose the moment vector into two components, which is perpendicular to the resultant force and which is parallel to the resultant force. Now, in this case, in order to find the position where there is or location where at which there is no in-plane component of the moment, we can easily find it by using the perpendicular component or in-plane component of the moment, which is mt, magnitude of the mt divided by fr. Then we will have one moment at this point, which is perpendicular to the, which is in parallel with the resultant force, and the resultant force, certainly this resultant force will generate a moment in this direction, right? Or in other direction, so it doesn't matter. So in this direction, yes, the resultant force will generate a moment in this direction, and certainly there exists a distance d. We can move the resultant force and the parallel component of the moment to a distance d at which the in-plane component of the moment will be 0. It will be much more clear, I think, when we solve some examples.